Good afternoon, everyone. My name is Tony Buzalaki, and I'm the president of the University Corporation for Atmospheric Research, or UCAR. Welcome to today's briefing on oceans and long-range weather forecasting. First off, I'd like to thank Senator Brian Schatz and his staff who are here for arranging this room for us today. Hope you had an opportunity to get some lunch. If not, please do so. For our format this afternoon, we're going to hear from our panel of 4 speakers, and then we'll open it up at the end for some questions from the floor. For those of you that are unfamiliar with UCAR, we are a nonprofit consortium of 117 member universities that grant advanced degrees in atmospheric science and related Earth system sciences. UCAR also manages the National Center for Atmospheric Research in Boulder, Colorado, on behalf of the National Science Foundation. The research that the UCAR community does helps to inform decision makers in terms of improving our predictive capabilities for weather, climate, water, space weather. And several times a year, we host these briefings here on the Hill to discuss the latest science and in areas of importance to policymakers here in the city. And so that brings us to today's topic. And we're going to hear from our panel about one of the major challenges in Earth system science going forward, and that is the development of accurate subseasonal to seasonal weather forecasts. Subseasonal to seasonal timescale are predictions of regional weather patterns from 2 weeks to 2 years in advance. And I often get asked the question, well, if we can't predict the weather beyond, let's say, day 7 or so, what's the basis for predicting patterns of weather 2 weeks, to 2 months, to 2 years in advance? And as you'll hear, the key to such extended range forecasting is a detailed understanding of the Earth as a coupled system, particularly the influence of the oceans upon the atmosphere. Now, I often draw the example where I think we are today as a scientific community where we were coming out of World War II. At that point in time, our knowledge of the physics and the dynamics of the atmosphere, together with the advent of digital computing, has ushered in today's era of numerical weather prediction, which is a multi-billion-dollar weather enterprise across the government and the private sector. And truly believe we're at that sort of verge today with respect to prediction of the Earth as a coupled system, providing actionable information to a whole range of societal benefit areas over the next several decades. And so improving longer-term forecasts is a national priority, and we've seen that in the Weather Research and Forecasting Innovation Act, which Congress passed last year, which emphasized the importance of seasonal to subseasonal seasonal forecasts. And as you'll be hearing, such forecasts are of vital importance to a range of public officials and business sectors. And essentially, every part of our economy depends on this particular timescale, all the way from agriculture to transportation. So federal agencies, private sector, academic community are all working together to improve such longer-term forecasts so that society can prepare for these changes in major weather patterns months in advance. And such forecasts will help to safeguard lives and property as well as strengthen our U.S. economic competitiveness. Our panelists today will talk about major new advances on this timescale and how potential improvements could be had going forward. So our first speaker is going to be Dr. Ben KIRTMAN. Ben is director of the Cooperative Institute for Marine and Atmospheric Studies at the University of Miami's Rosentiel School for Marine and Atmospheric Science. His research focuses on understanding and predicting climate variability on timescales from days to decades. In addition, he also leads the North American Multi-Model Ensemble Prediction Experiment, which is an innovative project that uses a number of weather and climate models to predict temperature and precipitation months in advance. Following Ben is GOKHAN DANABASOGLU from the National Center for Atmospheric Research, where he is chief scientist of the Community Earth System Model. GOKHAN is an expert in computer simulations of the ocean and the Earth system. His research focuses primarily on understanding the role of the oceans in the coupled Earth system's climate, through computational modeling of the oceans and the larger climate system. Next up will be Dr. Chad McNutt, who is principal and co-founder of Livestock Weather. Livestock Weather is a private company that provides livestock producers with advanced weather and climate information and analytics. Previously, Dr. McNutt worked for the National Oceanic and Atmospheric Administration, where he helped to develop the National Integrated Drought Information System, known as NIDIS, and worked with federal, state, tribal, and local governments to develop drought and early warning systems across the U.S. And to finish our panel, Dr. Alicia Carr is a climate scientist and associate director of research partnerships at Jitter Technology Systems Incorporated. Jitter, as we'll hear, is a private company providing data and analytic services for the management of climate and weather-related risk. Dr. Carspek's areas of expertise include assimilating data into oceans and ocean-atmosphere interactions into state-of-the-art global climate models. And we'll begin with Ben KIRTMAN.
Thanks, Tony, and thanks to all of you for joining us today. My job today is to really lay the foundation of answering this one basic question. Why do we think we can predict subseasonal to seasonal timescales? And Tony, I think, provided those essential timescales. We're thinking 3 weeks from today out to maybe a year or 2 years. And I want to make 2 points, 2 very simple takeaway messages. One is the subsurface ocean. So what's going on below the surface of the ocean is our essential mechanism. It's the memory of the future, or what's going to give us the future. And it's that evolution below the surface that tells us we can predict. And I'm going to show you a nice example of that, how that evolves over time, from an example I'm sure you've all seen before, a nice El Nino event. The second one, and these aren't necessarily mutually exclusive. They actually relate to each other. The second one is Airsea interactions at the ocean-atmosphere interface. So how do the oceans and the atmosphere talk to each other? How do they exchange heat and momentum and moisture? And that exchange of information, getting those feedbacks between how the atmosphere and the ocean work, that gives us predictive timescales. And I'm going to try to show you examples of that. How important are they? So both are essential for this subseasonal to seasonal problem, but I'm even going to make an argument at the end that even for weather, we need to consider these processes. So the classic example that I hope everyone has seen many times is the El Nino phenomenon. And this picture looks a little bit complicated first, so let me just sort of walk you through it. That plan view, that panel view that you're seeing, that's the depth of the ocean. So that's at depth. So it's going down to about 300 meters, and that blob that's in the red circle there, that's the subsurface temperature anomalies that's associated with up and down movements of the ocean thermocline. So there's a big warm blob in January 1997 then, and the plane view is the surface of the ocean surface temperatures. And so you can see in January 97, it's cold in the Eastern Pacific. Yet if you called me up on the phone, as Polish Newsweek did, in January 1997, I could have told you that an El Nino was coming. And that's because of what's going on below the surface. So let's look at that evolution. So there's the same picture over again. And so over time, here's April, a few months later, you can see that blob of warm water has migrated towards the east. And you even see that the cold water at the surface has disappeared, and there's a hint of warm water starting to appear in the Eastern Pacific. Go a few months later, that event is starting to really mature. You see the intensification of the warm water below the surface, and you see at the surface very strong sea surface temperature anomalies, and even stuff that's propagating up the coasts of California and Central America. And then we get to the mature state. This is a year later. This is January 1998, and you can see the event is very mature, real strong warm event. But below the surface, in the Western Pacific, is that memory, the future that's coming. That's the La Nina event. And as we go forward in time, you can see that cold water look like it's migrating or propagating across the basin. It's eating away at the warm water at the surface. And then when you come to September 98, you can see the cold water has penetrated the surface. And then finally, 2 years later from where we started, we have a cold event. So it's that subsurface processes in the ocean that provide the memory that tell us we can predict perhaps out to 2 years. Okay, so the second point I raised was this notion of Airsea feedbacks, how the ocean and the atmosphere talk to each other. So in this 3-panel plot, you want to think of the first panel there as being, that's labeled observations. Am I getting the gong? The first panel that's labeled observations, that's a measure of how the ocean and the atmosphere talk to each other in terms of heat, how they're exchanging heat. And so you see those bright reds, there's a big exchange of heat. They're going together. A lot of heat is coming from the ocean into the atmosphere. And in this panel all the way on the other side, it's not showing that red stuff. And that's because it doesn't capture the fine details of the ocean currents, the fine eddies that you see in the ocean. The middle panel is a simulation where we actually capture those eddies. And you can see that that discussion between the ocean and the atmosphere is captured, perhaps overdoing it, but it is captured when you actually simulate the fine structure of ocean eddies and ocean currents. Why does that matter? Let me show you another example. This is from a simulation of the Gulf Stream in the North Atlantic. And the top panel is that simulation that I just showed you before that doesn't have the fine structure, lacks that fine structure in the ocean. And the bottom panel is observational estimates that come from satellites. So this bottom panel is the truth. And you can see you have a nice tight temperature gradient between the north and the south. You can even see the warm water coming up from the Caribbean along the coast of North America. And those features are weak or nearly absent in the model that doesn't include the fine currents of the ocean. So let's add in the fine currents of the ocean. And you can see you recapture that north-south contrast. You can see the water coming up, warm water coming up from the north, looking much more, not perfect, but much more like what we see in nature. It matters because it affects how the rainfall distributes. So this bottom panel is observations of rainfall from storms that track across the U.S. and get moisture from the ocean and dump that off the ocean. And you can see there's this large rainfall right along that front in that bottom panel. That big high rainfall there that's sitting right on that front between the warm and cold water. Above, in the top panel above, the shading is exactly the same from that high-resolution model. So that high-resolution model that captures the ocean's eddies in that front, that's capturing the rainfall distribution appropriately as it's observed in nature. The model that doesn't capture that front, those are the gray contours. You can see it's sitting in completely the wrong place. So this tells you how important the ocean is just to get the day-to-day weather fluctuations right and to ultimately return the mean state of the climate system. You have to actually capture the details of the ocean. Let me give you another example. In this example, we're now looking at one of the most talked about and well-known phenomenon on subseasonal timescales. This is the so-called Madden-Julian oscillation. What is the Madden-Julian oscillation? It's a phenomenon that propagates around the globe in the tropics. And basically, there's a big blob where there's enhanced rainfall, and then right next to that, there's a big blob where there's reduced rainfall. And this thing propagates around the globe, and it takes somewhere between 30 and 60 days to propagate around the globe. And you can imagine, if I knew that was coming, over the Atlantic, and that when you have that enhanced phase where there's enhanced rainfall that could excite hurricane activity, that's something I would want to know. That's something I would want to be able to forecast. So this is a picture of an observed Madden-Julian oscillation, and it's a strange figure if you've never seen one of these before. I remember when I was a graduate student, it took me the longest time to come to understand these figures. But what it is the picture of what the rainfall, how that evolves along the equator. So in that lower end, that's the rainfall right along the equator at day 0, when we're starting out this forecast. And the blues and the greens are enhanced rainfall, and the reds are reduced rainfall. And over time, if you march up the page as the forecast day increases, that blob of enhanced rainfall propagates along the equator, moves further and further towards the east. That's the Madden-Julian oscillation. The panel on this side that's failing to capture that propagation, that's when I don't include how the ocean and the atmosphere exchange heat, momentum, and moisture, if I ignore those processes. And in the middle panel is how well I reproduce that observation when I use a model that does simulate the interactions between the ocean and the atmosphere in terms of heat, moisture, and momentum. And so you can see, to capture that propagation, that eastward movement, those Airsea feedbacks are essential. And the state of the ocean is critical to getting those right. One last example. This is now stretching into the weather timescales. This is looking at hurricane forecasts. This is a really nice example. And the top panel on this side here, that's showing you in the shaded, it's showing you the temperature of the ocean. And the black curve there is showing you the track of a tropical cyclone. And that's an example from a simulation or a number of simulations that don't include Airsea feedbacks. No Airsea feedbacks at all. None of that exchange of heat, momentum, and moisture. In the top panel on this side, it's showing you the same model, the same storm, but now where we include Airsea feedbacks. And so you can see there's this cold wake following the storm. And if you think about those Airsea feedbacks, think about warm water is going to flux more heat and more moisture into the storm. If you slow down that flux of heat, of moisture, and into the storm is going to be less intense. And this is showing you an example of exactly what that is. This is that flux of heat. The red curves are from forecasts where we didn't include the interactions. We didn't include that cold wake. And so you can see they way overestimate the heat fluxes. When we include those couple interactions, those heat fluxes are captured, right? Correctly captured. And what that leads to is a better intensity forecast. So the red curves correspond to the minimum central pressure associated with the storms when we don't include the Airsea feedbacks, and the blue and the black correspond when the black is the observed and the blue is when we simulate that. So the intensity of the storm is highly sensitive to those Airsea feedbacks. If the storm happened to propagate over a warm core eddy, like in the Gulf of Mexico, the response would be opposite, because this would be really, really warm water pumping even more heat into the storm, and so the storm could intensify. So getting those Airsea feedbacks is essential. So we have major efforts, really strong efforts. They're not enough, but they're a really good start at trying to take advantage of this ocean memory and these Airsea feedbacks to actually make subseasonal and seasonal predictions. This one project here referenced is a seasonal effort. This is the North American Multi-Model Ensemble, and you'll see some more slides from that. And this system actually became a NOAA operational system in 2016 and is driven by the climate research community to make better seasonal forecasts. This other project is called the Sub-X project. It's trying to capitalize on that success here and seeing if we can make those forecasts on subseasonal timescales using that same multi-model approach and in training both the operational scientists and the research scientists in trying to improve predictions. So let me close. 2 points. That subsurface ocean memory, that's why we think we can predict. And in order to get good predictions, we have to make sure we do a good job of capturing those Airsea feedbacks. That's the second point. And I would say that these are neither mutually exclusive, they're both essential, and they operate on not only the subseasonal to seasonal timescales, but they operate for forecasting from days to decades. Thank you.
Thank you. Good afternoon. So what I would like to do today is talk about computer modeling capabilities and challenges for Earth system predictions. First, I wanted to show you some examples of societal benefits of such weather and climate predictions and introduce the role of Earth system models that we use in such efforts. Then I wanted to show you 2 really promising examples of weather and climate prediction. It will be on the seasonal to decadal timescales, actually. Then conclude with some challenges in prediction efforts that we encounter and finish with a summary. So here's a list of, it is not all-inclusive list of some societal benefits of weather and climate predictions, broken down according to it is sort of time periods, time scales. From a few days, or even a day to up to a week time scale, we are all interested in knowing what the weather is going to look like. And I'm pretty sure that everybody in this room looked at the weather forecast for today, yesterday or this morning, to see whether they need a raincoat. And I guess you need a raincoat this afternoon. On slightly longer subseasonal time scales, and I'm talking about maybe order a month or 2 months here, we are interested in whether certain rain events or more precipitation will continue, or there will be drought conditions or extreme heat waves so that we can be ready for those. On slightly longer time scales, from season to intrannual, that's up to 2 years or so, we are similarly interested in weather events, again, extreme heats, extreme precipitation, blizzard conditions, so we can be ready. And then this also gets into resource management issues. If you're essentially predicting that there will be extreme drought conditions, then it's going to impact how people use their water resources. And similarly, for forest management, for example, if there are drought conditions, then there will be more likelihood of fires, and they can be ready if they know these in advance. And there are implications for agriculture and cattle industry as well. And especially on seasonal timescales, we are interested in knowing how the sea ice extent is going to change, particularly, for example, in the Arctic Ocean, because that has implications for shipping routes in the Arctic. On longer time scales, what I labeled as decadal, but this is covering essentially from a couple of years to 5 to 10 year time scales, similar issues are of interest to the society, water, fire, and agriculture and forest management. People are interested in infrastructure investments. So if you are going to build a dam on a particular river, you may be interested in the river flow estimates for the future. Natural hazard mitigation and adaptation is always an issue. And if you are predicting essentially that there will be extreme heat conditions happening over long time scales, that has implications for populations. And of course, socioeconomic strains are associated with all of those predictions. And finally, there is great demand from insurance industry, essentially knowing weather and climate into the future so they can be better prepared. There are three fundamental blocks of predictions. The first one is observations. They can be satellite observations, in situ hydrographic observations, but we need observations. We need computer models to perform advanced simulations of the Earth system on supercomputers. For National Center for Atmospheric Research, we are using our supercomputer located in Cheyenne, Wyoming for this purpose. And then the third block is essentially what I labeled as initial conditions. It is bringing the observational block and the modeling blocks together to obtain our best estimate of the present state of the Earth system. So if we start our predictions, weather and climate predictions, with a really good estimate of the present state of the Earth system, we get better predictions of weather and climate into the future. And this is an extremely important step, and it includes, for example, what we call data assimilation. It's like a marriage of observations and models together to produce a consistent estimate of the current state of the Earth system. So as I indicated, the computer models that we use are the global Earth system models. They are the primary tools to make these weather and climate variability forecasts or predictions. They use physical equations to represent key components of the climate. That can be atmosphere, the land, the oceans, and the sea ice. And they essentially simulate key fields, such as temperature that we feel in our everyday lives, or humidity, and that can be rain or precipitation. And the schematic down here is essentially showing what the global Earth system models are trying to represent in their frameworks. In addition to components, you can see, for example, clouds, precipitation, snow, land use are all included in our models. One such model that I'm quite familiar with and I use quite often is the Community Earth System model. It's based at NCAR and is primarily funded by the National Science Foundation as well as the Department of Energy. It is a community model. We are developing it in collaboration with community, and all of our simulations and model solutions are available both to the university community or to the public sector. And the schematic is showing an example, is showing the component models that we have in the system: atmosphere, sea ice, land ice, oceans, surface waves, river runoff, and land are all incorporated, and they communicate with each other. So it's a coupled system, and we are after a coupled modeling framework. So using this particular modeling framework, for example, I wanted to show you two examples of the community climate prediction efforts. The first one was already introduced by Ben. It is the North American Multi-Model Ensemble, NMME. It's primarily funded by NOAA. It's targeting shorter time scales, subseasonal to seasonal. The second effort is the decadal predictions that we have, and these are, again, they can go from seasons to up to a decade, and it is representing both a national and international collaboration effort. So what I wanted to show you is essentially one example of promising forecasts or predictions from both of these efforts. The first one concerns the surface air temperature predictions over North America. I should mention that before an important step in our prediction framework is the verification of the solutions. We need to be able to verify our model and the framework to see whether it's actually producing existing climate events, existing observations, so that we can have confidence in our forecast into the future. And this is an example of verification. On short timescales, it is essentially trying to see whether the NMME system can produce with confidence January mean surface air temperature over North America. So the plot on the left side is from an older version of the model. That's roughly from 10 years ago. And the plot on the right is essentially from a newer version of the model. It includes lots of improvements in the modeling system itself, but also inclusion of more and better, we think, observations. Red colors indicate here actually good skill. That means our prediction system is actually matching what the January mean observations told us in surface temperature. And it's a rather rigorous skill test. Values of 0.2 actually is quite meaningful here. And you can compare it to the blue colors that we see in the older version. The message that I wanted to convey here is that better models and better, in this case, particularly ocean initial conditions, can indeed produce better surface air temperature predictions over North America. And I think that's an important point to make. The second example is for longer time scales. It's prediction of 10-year trends in Arctic winter sea ice extent. And as I indicated, this is important essentially for shipping routes. It's a complicated plot, but I just wanted to walk you through it because it's important to show you how we are doing. The time series plot is from 1950 to present, roughly. The blue lines are actually observations. We do have satellite observations starting in 1979, and each dot represents a 10-year trend. So, for example, the last blue dot was plotted there 2006 or so, but that's a 10-year sea ice trend from 2006 to 2015, roughly. We can compare our decadal predictions, that's the red line there, to observations to verify how well we are doing. And then you can see quite a nice match of the observational decadal trends with our decadal prediction system. And I was stressing the importance of verification, and the panels on the right actually show that. The bottom one is what the satellite observations showed us in terms of trend between 1997-2006 period. Blue colors indicate that the sea ice was declining in those areas. And if you look at the top panel, you can see in the same areas, our decadal prediction system is essentially saying that the sea ice is declining during that period. So gaining confidence from previous, what happened in the past, we are actually, if you look at the last part of the time series without any blue dots, that's our forecast. And we are forecasting essentially sea ice conditions in those regions will not change from what it is today over the next 5 to 10 years. So that's an actual prediction. There are, of course, challenges. One of them, as I try to stress, observations are quite important to get the best state representation of the climate system today. We need really good models at high resolution, so that requires model development and good fidelity of the models. There are technical limitations that I don't want to get into here. And then final point is quite important. These are actually quite resource-demanding applications. People's time, computational time, and the data storage. And finally, I would like to finish with a quick summary. Global Earth system models are the primary tools that we use for weather and climate prediction. Existing prediction efforts show promising results that are beneficial to society on many time scales. To improve predictions, better models and better, more observations are needed to produce better initialization of the framework. And it is really important to maintain and sustain efforts in both observations and model development. Thank you.
Okay, good afternoon. It's good to be back. I worked for NOAA for about 12 years, so coming back and seeing a lot of friendly faces has been really nice. I'd like to thank UCAR, Tony and Scott for inviting me. I really appreciate being here and talking a little bit about what we've been up to for the past year. So again, my name is Chad McNutt, and I'm a co-founder of a company called Livestock Weather. I'll just move on. And so what we do is sort of like what the name implies. We provide livestock producers with weather and climate information, and we try to contextualize that information so that they can use it in their decision making. We were founded last year, and I guess I'm here to sort of talk about why subseasonal to seasonal forecast is important to us and how we can actually provide information to producers in a way that actually saves them money or has economic implications anyways. So I'm going to give you two examples, and the first is looking at the ongoing drought in the Southern Plains. So it's really having some pretty big impacts in Kansas and Oklahoma, in the panhandle of Oklahoma and western Oklahoma, and the panhandle of Texas, and into New Mexico. And then I'm going to talk a little bit about Hurricane Harvey will be my second example. And so what you're seeing up there, the top image is the U.S. Drought Monitor. I believe it's the most recent one. And you can see the area I'm talking about in kind of the reds and purples. And then Hurricane Harvey, the map shows two different forecasts. They're 5-day forecasts, actually, so it's a little outside of our subseasonal time frame, but I think it's still okay. And then the colors, those warm colors, are cattle inventory. So warmer colors indicate higher cattle numbers. So you can see kind of where cattle sort of sit around the U.S. The largest cattle producing state is the state of Texas. Second largest is Nebraska, followed by Kansas, California, and Oklahoma. So when you have a drought in Kansas, Oklahoma, and Texas, you're hitting a large percentage of the cattle population. So again, the image on your left is cattle inventory, again, and just a little closer up image. But on the far right is winter wheat, and that's in acres harvested. So winter wheat is important. The reason I'm showing winter wheat is because cattle producers, it's a fairly big strategy of theirs to graze winter wheat in the fall and into the winter and part of the spring. And so in Kansas, again, Kansas, Oklahoma, and Texas, it's a big strategy. And when they don't have winter wheat, they have to do something with their cattle. And a lot of times that means sending them to a feed yard where it sort of accelerates the process and they get into the beef cycle much faster. And what that does is it speeds up supply, which is sort of what's happening right now. So what happened in 2017, we had quite a bit of rainfall in August and September. Everybody thought it was going to be a good year, but at the same time, La Nina was sort of on the horizon, and the forecasts were indicating that it was going to be there was going to be a La Nina to develop in the fall. For those that don't know, the Southwest, or Texas and Oklahoma in particular, have a very strong connection with El Nino, or La Nina, well, both, El Nino and La Nina. La Nina winters typically tend to be warmer than average, and also precipitation is less than average. So what I'm showing you up here, these are 6 different La Nina events, starting with 95 to 96, all the way to more recently in 2010 and 2011. And then in parentheses is the harvest for winter wheat, and that's in bushels per acre. And there's quite a bit of variability. So again, the darker kind of purples are higher acres harvested, and the lighter colors are lower values. So you can see in 2010 and 2011, they had a fairly bad crop. Averages about 30 bushels per acre. They had about 17 bushels per acre harvested. Other years, it's been pretty good. It's been about average. I'll tell you, in 2018, this year, it may surpass or actually be less than the 2010-2011 value. So it's going to be pretty nasty. So we put this graphic out around November, and we started looking at these analog years for winter wheat. One of the big challenges with that is you can see the variability, and we know that there's a strong teleconnection between La Nina and this area of the country, but it's the variability that really matters. So anything that we can do with those forecasts to get better understanding about, and it's as hard, about timing or at least variability, that could go a long way to saving these folks money. The second example I wanted to show is a product that was developed at NOAA and also at the International Research Institute for Climate and Society at Columbia. And this is a little technical, but it's the Standardized Precipitation Index. And for those that aren't drought nerds, this is one of the biggest drought indicators that we use to monitor drought in the US. And there's a very simple reason why, because it's a very simple index. It's all based on precipitation. And the reason why a lot of people like it is because you can look at precipitation in a lot of different timescales. So there's I guess, as famous a climatologist as you can get, Kelly Redmond, who's at the University of Reno, or University of Nevada at Reno, used to say that you can have a drought inside of a medium-term wet period, inside of a much longer-term dry period. And that's really what this index gets at, because you can look at precipitation, and it's measured against what you would expect for that time frame. So you can take a week's worth of rainfall in a particular week, and you can compare that to what you would expect for that week. So it gives you sort of a deviation from normal. You can also look at it at a month time scale, or 3 months, or 6 months, or even up to 6 years. So you can kind of get at that question about where are you in the time frame that you care about. And for cattle producers, I can tell you it can be 6 months, it could be less than that. But right now, we're interested in the 6-month time frame because particularly in Texas and Oklahoma, they care about what happens between October and now. They're just now getting into their wet period. And so in the wintertime, they really care about recharging their soils. And so what I can do with this standardized precipitation forecast, it's not just the indicator, but it's actually the forecast, and it looks at a month out. And what you're seeing here is actually a lead time of 2 months, is that I can take that information and then with some simple demographic or production data, we can start developing like risk models. And so what you're seeing the map below is looking at this SPI forecast, and I can say, is it going to get drier or is it going to get wetter at a time scale that I care about? In this case, it's 6 months. And you can see the reds actually have high cattle density and they have high drought intensity as well. And so what we can do is take this information and communicate with our producers that we work with. The last example is on Hurricane Harvey. As the storm was sort of bearing down on the Texas coast, there was this realization that there's a lot of cattle sitting in the path of that storm. So one of the things we did, along with Texas A&M, did the same thing. We started putting out the amount of cattle that that were in the forecast track. It turned out it was about 1.2 million head of cattle. And so what happened, just a day or so before the storm, people sort of got into action. And what you're seeing in the lower image there, that's in Dayton, Texas. That's northeast of Houston. They're moving their cattle as the storm is hitting. So there's a pretty good bit of damage, but it could have been worse. There's about $93 million in damages to the livestock industry, not just to cattle, but to other livestock producers, including infrastructure like barns and things. But simple analytics like that went a long ways. And I don't know if anyone remembers some of the press around that time, but they really liked that 1.2 million number of head of cattle. And we don't know for sure, but we hope that did something. We have a number of producers that we communicate with, and we hope that putting out very basic analytics like that actually help these guys make their decisions. In the lower image of part of the slide, that's a quote from David Anderson, who's an economist at Texas A&M. And he just says, overall, these livestock numbers could have been far, far worse had it not been for the quick action of ranchers ahead of and during the storm. So if we're talking about subseasonal predictions or even within 5 days, having better forecast tracks go a long ways for these producers making decisions about something like a hurricane in their path. It's not easy to move cattle, right? So it's not something you want to do if you don't have a good feel for the forecast. Okay, so just to summarize things, surprise, we need more sustained support for the subseasonal to seasonal forecast. I should have mentioned that Standardized Precipitation Index forecast is part of this North American multi-model ensemble that Ben had mentioned. It uses six of the models from the NMME, so we are using it. these things do have real economic implications for ag sectors like the cattle industry. I mentioned that not having winter wheat it's caused, it's contributed to the oversupply in the cattle industry, and we're seeing that now. I don't know if anyone's looking at prices on the Chicago Mercantile Exchange, but prices are not doing good, and people have described that there's a wall of cattle coming at them. And what's happened is people that relied on winter wheat had nowhere else to do with their cattle, so they sent them to the grow yard or the feed yard, and that's accelerated the process. And so we're in an oversupply situation. There's other reasons for that, but the drought is a big part of that. Right after Hurricane Harvey hit, cattle futures went up by 2.5%. So in addition to people moving their cattle, traders and things, there's money to be made for understanding how, what sort of impacts are going to be to the industry. So again, these are two simple examples. There's lots of other analytics that we're looking at. Some of it has to do with seasonal forage growth. You can even look at pest and pre-deployment of pesticides. We're working on a model for hornflies is a good example, that causes a lot of economic issues for cattle producers. And then the last thing is looking at carcass weights and estimating based on rainfall and forage production, what carcass weights might look like, which also has an impact to the industry. So I think that's my last slide. Thanks.
My name is Alicia Carr, and I'm a climate scientist at Jitter, which is a private company, which I'll tell you a little bit about. And I wanted to share today with you some perspectives on the partnerships that can exist between the research and the private sectors, and how we can work together to provide climate information that has high social and economic value. Prior to coming to Jitter, I worked for about 10 years at NCAR, so it's a really great pleasure here to be here with my ex-colleagues, and thank you also to UCAR for having us here. So just a little bit about Jitter. So Jitter is an early stage company. We were formed last April, so we're about a year old now. We are based in Silicon Valley. Our science offices are in Boulder, Colorado, and also New York City. And our focus is on providing climate and weather risk analytics at time scales all the way from weeks all the way to decades. And so being here, we really view the subseasonal to seasonal as an important piece of this spectrum of future condition information that we can potentially provide for our clients. So as we move forward, I'm going to be talking a lot about just climate information in general. And when I can, I will specify which of it is relevant to the seasonal to subseasonal problem. So we've been talking already, and you've seen some examples here about how climate information can have utility across a broad set of sectors, from business to finance to government. And we know that, for example, weather information in the US has huge potential economic value. Estimates range between $13 to $30 billion a year in value for weather information. But it's actually very difficult, and we don't know yet how to quantify the economic value of climate information. And so there's a great deal of market discovery that's still required, which is part of what the private sector is doing during this time, trying to discover those markets and foster those markets for this valuable information. So I want to just give you a little flavor of one of our products that we've been developing in one of our pilot cities of Charleston, South Carolina, where we've been looking at flooding. So our product is called Flood Score, and it provides clients information on how their risk of flooding may change in the context of future environmental conditions. In this particular example, we were focusing on the effects of coastal sea level rise. And on your left, you'll see this plot here, which is a map of the flood risk in Charleston, South Carolina. And you can see that, unless you can read that, it brings together natural features, natural hazards, constructed features and infrastructure, and also the climate change variables. And this is an important thing to keep in mind, is that one of the things the private sector is doing in this context is adding information that's not just physical variables. What comes out of climate models are very often physical variables, and we are really layering on top of that other modeling and other information in order to make that useful. Another piece of information that's really useful for this audience is for us to point out that we relied on a lot of open source models, simulation sets, observations, and basic research that's funded by federal agencies. Okay, so here is just a non-exhaustive list just for this product of the agencies that supported this work. So you'll see here Department of Energy, Department of Defense, NOAA, NSF, Army Corps of Engineer. I think that's everyone on this list. So these are really valuable relationships for us to have. And so we are very, very aware of how important it is to be cognizant of this pipeline between the discovery and invention that's happening in the research sector, all the way through the creation of the commercially viable tailored products, which is what we do, in order to create this focused climate information so that users can actually take into consideration future changes when they're making decisions. So because that we know these relationships are so important because they just provide essential information for our business, we are very conscious of what kind of engagement we want to have with the climate science community and how we want that community to engage back with us. So in terms of how we engage with the climate science community, we actually have it as part of our core business strategy to have this engagement with the research community. And we do that in three primary ways. One is through direct sponsorship of climate science research. We do that through something called the Jupiter Community Science Program, which just launched a few weeks ago. We foster collaborative R&D between our scientists and also research scientists who are in the academic sector. And also we connect private and philanthropic funders to promising research programs, trying to make those connections. And also just being here to try to talk to you about the value of the information that's coming out of federal agencies. And then this is about what we believe makes climate forecast data viable for commercial development. So you can think of this as our primary request from this community about what's going to help us market this information. And we have three primary aspects to the information that really help us do a better job at marketing it. One is to have high quality climate forecast data coming out. Another is to have climate forecast data that is easily accessible, which doesn't just mean free. Okay, easily accessible is actually our ability to practically get it. And the third is to have reasonable assurances of continuity through time. So products that we believe that if we invest in these products, they're going to be available over time. And so Jupiter, in general, supports funding into programs that promote these outcomes in terms of climate information. So let's just talk about a little bit about quality and what that means to us. And you've already seen this plot on your left here. I believe that was in GOKHAN's talk. But the general comment here is that the higher the quality of the climate forecast, the easier it is for us to serve markets and expand those markets. Okay, so when you make better products, it's easier for us to sell them. And so in order to do that, these are key focal areas for federal funding that we believe will help accomplish those goals. And some of these we've already touched on before, which is basic research into climate variability. Okay, so not just climate change, but also climate variability on these subseasonal scales and these seasonal scales. Sustained climate observations, you've heard that again as well. This is for process study, it's for model validation, it's for forecast validation. And another point that GOKHAN brought up, which is for forecast initialization. Okay, and not all observations are created equal. So in terms of forecast initialization, for example, subsurface ocean observations are some of the most valuable, much more valuable than satellite observations in this context. A third, coupled model development and coupled data assimilation. So this is not just model development into more atmospheric models, but it's concerted development of ocean models, land models, sea ice models, and also the data assimilation systems that we can use to initialize these forecasts. And fourth, and very important, is the actual money that goes towards funding people who are engaged in prediction activities. So doing the job of prediction takes a lot of funding. And that's not only for doing real-time forecasting, but also retrospective forecasting and the scientific analysis of forecasts that allow those to improve over time. So let's talk a bit about what we mean by accessibility now. And there is what's often termed the paradoxical crisis for the usability of climate science data. And that is that the more sophisticated the models become, the harder it is to use them. And that happens for many reasons, but mostly it's because Earth systems models are becoming more complex and larger in size. So the data sets are actually getting much larger. And GOKHAN talked about how to do this problem, you actually need a coupled model, which means you need to bring in the land, the ocean, and the atmosphere. So you actually have a larger model, you have more data coming out of that model to do this problem. People are coming up with more and more complex processes and representations of processes in those models. They're being run at higher resolution, and Ben touched on this quite a bit, which is that you actually have more process fidelity in some cases when you're running at higher resolution, making bigger data sets. And also people are running with larger and larger ensemble sets, okay? So forecast skill tends to go up when you have larger ensemble sets. We already know this from NWP. It's also true for the subseasonal to seasonal prediction. And so all of these trends are going to basically increase the data volume that we're dealing with here. And what that means is that data management and distribution should not be an afterthought, okay? We know these things are coming down the pike and they need to be thought about. So just for anyone in the room who's doesn't typically think in terms of data volumes, I just want to give you a little rule of thumb here, which is that when people start to talk about data sets that are greater than 1 terabyte, what you should know is that a lot of people had to think hard about how they were going to produce that data, store that data, access that data, distribute that data, okay? So once you get into those data volumes, you really have to start thinking about how you're going to deal with that data and manage it. And as a point of context, the NMME, which has come up multiple times here, that is about 1.5 petabytes, okay? So that's about 1,500 terabytes of data, so that's a lot of data there. Another example up here, which is not particularly about subseasonal, but generally about climate data information. This is from an example from our partners at AWS, where there was a use case around processing about 10 petabytes of Landsat data. Landsat data is a satellite data source. In this case, it was used to look at vegetation. And this was looking at tens of thousands of cycles where they had to repeat the same process over and over again. And they were able to bring the cost of that in time, that's seconds per calculation, from 375 seconds per calculation to 75 seconds per calculation, just by changing the data storage patterns associated with that. So what that means is that someone had to sit down and think about what the use case of that data was going to be, and then design the storage so that it supports those use cases. And so that really needs to be a focal point when we start to think about the data access bottlenecks. Another one is actually the generation of software for faster access and subsetting and analysis of large data sets. There are actually great programs that happen out of NOAA, NSF, DOE to do exactly these things. Happy to share them with you after this. So more funding into those types of projects. And of course, again, what GOKHAN mentioned is more boots on the ground to manage data and respond to data requests. This is typically a place where it's a real strain on science agencies who want to be doing science when they have to be dealing with data requests. And the final ask of the private sector has to do with the way that we have continuity of data and continuity of our relationships with the public sector. We want those relationships to be open in terms of communication and dependable in terms of receiving this data and trying to understand what is the state of the art in the science. So again, this looks like communication by federal agencies about what their plans for supporting and extending climate prediction research, excuse me. We like to have private sector input into funding priorities. That's one of the things that I'm doing here, is giving you input about what we think are the important funding priorities. Consistency and timeliness of data delivery. Once a product becomes operational or semi-operational, we want to know that it's going to continue to be there, at least for some reasonable amount of time. And again, continuity and longevity of data streams. So I'm going to just close there, back with these 3 core tenets of things that we would like. And again, please approach me if you'd like to talk more about our view on this particular science endeavor and the funding that could potentially support it.
So thank you, Alicia. And we have just about 20 minutes of time for questions from the floor. So please step up and state your name and affiliation.
California. 2015, an El Nino was forming in the Pacific. In 2015, an El Nino was forming in the Pacific, and NOAA had a lot of conference calls with members of Congress, with our water agencies out in California, and so because of that, Congress appropriated extra funds for flood control and water capture facilities out in the West, and local governments and state governments did the same. And in that 15-16 water year, it was below average rainfall. And then in 16 and 17, a La Nina was forming out in the Pacific, and that 16-17 water year was a dramatically above average rainfall. Now, thankfully, some of those funds that were put in place in the year before were permanent, so they were able to address that 16-17 rainfall. Some of those funds that were put in place from the previous year, though, were for emergency flood control abilities, and so they weren't there for that next year. So I guess my question is, what happened? I'm guessing that's directed at me. We're not 100% sure exactly what happened, but this is what I think is so important about experimental prediction research: is the real-time experience of what actually happens. We learn a tremendous amount about what our capabilities are, where we succeed and where we fail. There are on the table at the moment 3 or 4 different competing hypotheses. I have my own. I'm trying to get research funds to test those hypotheses as to why the California rainfall didn't happen when it was supposed to happen. I assure you, I was very concerned. My father, who lives in Santa Barbara, California, called me every week and said, "Where's the rain? You said it was going to rain. Where's the rain?" Every week for an entire season. So I acutely feel the concern that sometimes forecasts fail. And that's also part of the problem, is that we haven't done a good job of explaining what the uncertainties in the forecast are, and that there was a significant non-zero probability that it would be dry in Southern California during the 15-16 El Nino. And so we need to learn how to better communicate those uncertainties and account for those uncertainties. And we also need to better understand, why didn't it happen the way we thought it was going to happen?
Thank you, Ben.
If you have a question, raise your hand. I'll bring the mic over.
Just another comment about that, which is, I think the other thing is that the private sector really can play an important role in navigating those types of conversations. And wasn't on my slide here, but the private sector can play a kind of an information brokering role, where you're learning about what it is that users of this information are concerned about, how they actually perceive uncertainty, and then try to link that back to what's coming out of the research sector, and to try to bridge that gap in a way that allows users just to continue working on their hard problem of decision making. That's a hard problem. And the scientists continue to work on their problem of making better forecasts, an incredibly hard problem. So there's this space in the middle the private sector can try to bridge that gap.
I didn't realize that I'd ever need a microphone. I haven't before, but I'll keep my voice down. Dr. Karspeck, thank you so much for your comments on the assimilation problem. It's honestly the first time in 18 years that I've been dealing with these issues that I've ever had them laid out for me in quite that clarity. I'd like to just sort of bop it back to Dr. I apologize, DANABASOGLU. Did I get that kind of right?
That's pretty good.
If I could ask you to sort of accumulate on Dr. Karspeck's comments, because you had mentioned it very, very briefly, and I feel like you might have some interesting ideas to supplement with.
Just just to make sure that I understand the question, are you talking about the resource part or something else?
honestly, like I said, it's the first time I've ever had it really presented to me in 18 years, so there's really nothing that you can say that wouldn't be interesting to me.
Okay. So I assume that that is the question. So the thing is that at the last, on that list in terms of challenges, I listed human resources. That's essentially, the forecasts, weather and climate forecasts, they essentially require a lot of people to put together observations. The models themselves that we use for Earth system prediction, or Earth system models in general, they are tremendous models. They incorporate so many things in them, and there are quite a lot of people, over 100 people, for example, behind our community Earth system model. And then we also need a similar but somewhat different framework, what we call data assimilation, that essentially is the marriage of observations and the models themselves to produce our best estimate of the current state of the climate so that we can essentially make reliable future weather and climate projections. So those are really high demand for human resources. The second thing is that these models, as Alicia indicated, they are getting more and more complex, and they require more and more computer power. And they require many, many ensemble members. Each forecast requires 10 to 30 or even more ensemble members for get uncertainty estimates. So that's essentially big-time computer resource. And then the third one that I listed was the storage. And that is essentially accessibility of the data sets. And that's becoming more and more challenging because the data sets are big, the ensemble member sizes are big, and they need to be easily accessible for analysis purposes. So, and then the continuity is another thing, because what we do is essentially subject to availability of funds, like NMME or decadal prediction efforts. And we need to be able to make sure that those efforts actually continue into the future, because if we are going to have a fruitful partnership with private sector, as Alicia indicated, they need the continuity of those data sets, and we need to be able to continue those efforts. Do you want to add more to that? Yeah.
So when I was at NCAR, I worked on the ocean data assimilation system there. And just want to give you some context about why the concept of data assimilation, maybe you've started to hear it come up more in the context of climate than you have in the past. And so some of that is, it's important to kind of understand that the climate community has not always had this idea of initialization baked into what it's doing. NWP has that baked into what it's doing. It's always been known that they have to have resources that are devoted to data assimilation, full systems. They're systems, just like a model is a system, right? But that is something that is more recent for the climate modeling community. So CESM, for example, is working really hard, I hope.
Yes, we are.
To develop these data assimilation systems to support their incredible model, right? They've developed an incredible model, but now they want to use it for prediction. They have to build an entire system for data assimilation. And that system development is tons of software engineering, a whole new level of research and expertise in that problem. So it is a really big challenge to bring initialization into the climate community. And the other big challenge of that is it's not just the atmosphere. It's the atmosphere and the ocean and the ice and the land, all of those. It is arguably as hard or harder than the NWB problem to think about initializing.
And how all those components talk to each other is critically important and a difficult part of the data assimilation problem. And we honestly don't really know how to do that very well.
Yes.
Peter Folger with the Congressional Research Service. Dr. Carspec, at the end of your talk, I think you said that the data you collect sub-ocean is more valuable than what you collect from the satellites. And I was hoping you could elaborate how are we observing the sub-ocean? What types of instruments? What's that look like right now? What's that going to look like in 10 years? Who's doing it? And where's the future of that endeavor?
Right. So, that was my statement about the value of subsurface versus satellite. So there might be people who disagree. But you can imagine that the issue is that mostly, and I'll give you an exception now, mostly what satellites are observing is the surface. So in terms of subseasonal to seasonal prediction, and I'll focus on seasonal because this is kind of the El Nino problem, sea surface temperature actually is very, very valuable, okay? But it's also well observed, okay? We're fine with that. And part of the reason it's so valuable is we have methods through data assimilation to make inference about the subsurface based on surface SST, sea surface temperature. Okay. Nevertheless, it is not as valuable as actually having direct in situ observations of the subsurface. And the primary way that we get that now is basically through XBT, so what's called an XBT. It's like an instrument that's dropped down. And then an amazing data set that's come online since 2000s, I believe, is the Argo profiling floats. And I'm sure many of you have heard about Argo. Argo is funded internationally, but primarily out of NOAA here, maybe another agency. I don't know. I think it's mostly NOAA. And it's transformative, right? Because it's really the first observations of the ocean that have routinely gone down to 2,000 meters. And more we're understanding that the deep ocean actually is playing a role in especially the decadal, prediction problem. Yeah. But one other piece is that there is a satellite observation that does give us some information about the subsurface, and that's altimetry. So that's sea level height observations, which is giving you an integrated sense of what the temperature and salinity are underneath it. But in order to use that, you need an amazing data assimilation system to ingest that data because it's not a direct observation of the thing that you want.
I just wanted to add also on longer timescales, or a few years to order a decade, we think that most of the memory of the climate system resides in the ocean, and that's the deep ocean. And probably you have heard of the thermohaline circulation. It's collapsing or not collapsing. There are movies about it, and what we call Atlantic Meridional Overturning Circulation, AMOC. And in order that, our thinking is that that circulation pattern in the North Atlantic plays a major role in essentially containing the memory of the climate system. And that transports heat from the low latitudes to high latitudes. And that's why if we can initialize that thing, the structure associated with that temperature and salinity distributions at depth, that is going to provide us actually the memory that we need in initialization with data assimilation systems.
I want to make one more comment about Argo that's interesting. So there are about 6,000 to 7,000 Argo floats that are out routinely. They cost about $15,000 to $20,000 per to put them out there, and then maybe to maintain $1,000 a year? No, more? I don't know what the maintenance costs are. But what's been interesting is that private companies, philanthropic companies have started to invest in purchasing these profiling floats and putting them out there, which is also very wonderful turn of events. Okay, so I hope more and more of that happens, which is that these really, really valuable data assets are now being supported by the private industry.
Good afternoon. My name is John Millay, and 5 years ago I sat up there, gave an impassioned speech about the need for funding for the GOES and JPSS weather satellites successfully flying today. So I'm a retired Navy oceanographer, or retired from Lockheed Martin, but today what I do is go out and talk to the public. 1 week ago, I was on a big, white, beautiful cruise ship giving lectures on ocean science and atmospheric science off the coast of Ecuador and Peru. And the people I talked to clearly had never heard about the significance of El Nino before, and then they went ashore and every tour guide told them that it's life and death when an El Nino hits. So here's the point. I can't be on every cruise ship, although I'm trying. How are we going to communicate to, I'm communicating to senior citizens who are affluent and who vote. How do we get the message to people who vote that we need the observational systems, we need the models, we need the investment in research? I guess my question is for you scientists is, what connections do you have in UCAR to really messaging to the public? Thank you.
So let me take a stab at that. given that we do have 117 member universities, we actually coordinate with our member institutions with respect to outreach and education. At the Mesa Lab at NCAR, we have a weather and climate exhibit. We're actually developing a roadshow where we're going around to the community with respect to resilience at the community level with respect to climate change. So again, it's almost a hub and spoke model. There's certain things we can do at the national scale, but everything is local. And so just as we heard from Chad with respect to the impact in Oklahoma, Nebraska, Kansas, et cetera, that's how we're working with our member universities to tailor these messages. And it's not, you know, me as president of UCAR that's speaking, it is that graduate student, that professor from that community. I think that's the greatest impact is when, you know, the local, the private sector, the politicians from that region, when they can identify and resonate with a member from their district. Every year we're now running, we'll be here for our board meeting here in June. We've done a national contest where we're choosing undergraduate and graduate students from across the country. Why is it important to communicate weather and climate? And we choose an essay. Last year we had 6 all-women scientists. It was great. We went up on the hill. We went with James, et cetera. And the PhDs kicked back and didn't say a word. It was the young students that were carrying the message to the point that in certain offices, staffers were running down the hall to follow up with the contact from their district to get more information. So that's kind of the different approaches we're taking to address this problem. Thank you, John. Thank you. So I think we're about at the end of our time. And so let me just close this up in saying, I think what you've seen today is that the taxpayer investments in Earth system science are actually paying off, delivering actionable information, making progress on this timescale of subseasonal to seasonal forecasts. But I think what you also heard here is some discussion and concern about what are the needed next steps to sustain this activity? What is the context and the construct going forward in order to maintain, as Alicia said, the quality and the accessibility and the continuity of this information? And in some sense, we've benefited from the progress in basic research, and we've jumped to some demonstrations of quasi-operational aspects of it. But this enterprise on this timescale is not sustained, all right? So we don't have sort of that construct in place to do the trade space and the evaluation, and we just started discussing here, of ocean observations in situ versus space-based, or ocean versus land versus stratospheric observations versus model investments, data assimilation for the coupled system to start doing some observing system simulation experiments. And so that operational pull is not yet there to sustain this activity and then guarantee that pipeline that the private sector is so dependent upon. So again, for us, it's a very exciting time, much more work to be done, but if, again, peering into that crystal ball, I think you're going to see some rapid changes in the years to come as we work as a community across the various Earth system disciplines. So again, my thanks to the panel and my thanks to all of you joining us today, and they'll be around for further questions. So thank you all.